Okay, welcome to this course called Foundations in Mathematics. My name is Jay Dittenberg, and let's get into it. So first of all, what is this course? This course is designed to be, and let me just make sure you can see. This course is designed to be an introduction into the axiomatic methods involved in mathematics. So if you've ever opened a mathematics book from a university or from a library, you may have seen something where you have the structure of a definition, a theorem, and then a proof. And this is essentially the basic structure of what's called the axiomatic method, meaning that we start with an agreed upon definition, and from that, we're able to deduct properties that we think are likely, called theorems. And then using the framework of propositional logic, we prove those theorems and learn more about the mathematical object or structure that we're trying to study. So we're going to learn mathematical notations. So there are a lot of shorthand, basically symbols that we can use that will allow us to write proofs and without writing a lot of words, basically. And they're pretty universal notations. One of the things about math is that you'll find we have like several words for the same thing, which is sort of frustrating sometimes, but the notation kind of takes it, makes it a little bit easier to write things out. We're going to study propositional logic. This is basically the language of mathematical proofs. And so we'll look into this in great detail. Reading and writing proofs. So when you study mathematics in the university, and actually even in geometry, but in geometry, it's sort of like in high school geometry, you do proofs, of course, especially if you take Euclidean geometry. But in that setting, it's sort of like you have the training wheels on, in a sense, which is good, definitely good. It helps you to have exposure to the axiomatic method and to logic, and to justifying every step in your proof. But there are lots of other types of proofs that you'll be required to create, to manufacture in various different majors. So one of the types of proofs we're going to look at is direct proof. This is probably the simplest type of proof, where you simply do a calculation or do an evaluation. It's very, very straightforward. Then we have proofs by contrapositive. So we'll talk about what the contrapositive is when we get into propositional logic. Proofs by contradiction. Also, again, we'll exploit the framework of propositional logic to be able to write these two different kinds of proofs. And then we'll talk about element chasing. This is a very popular proof method in set theory. And it could be sort of any combination of these, but the idea is that when we're trying to prove something is true about sets, we assume like, okay, so the element is here, then what does that mean? Basically, we follow the element through the various different sets to see what we can conclude from that. So that's called element chasing. And we'll do that. We'll look at a very characteristic proof, a very popular proof of De Morgan's law in set theory. And also it's used in probability. Let's just say set theory is, similar to probability in that in probability you have sets, but we have a special name for the sets called events. And maybe you'll see that someday. And then we'll look at if and only if proof constructions. And these are the type of proof where people say we have to prove it in both directions. And you'll see what we mean by that. So who's this course for? Initially, it's for mathematics majors, because when I went to university, I was really good at calculus, and I was even really good at differential equations. I think the second time But I did actually, I got like a 97% in differential equations. And so I was very familiar and comfortable with applied mathematics, I guess you could say. And when it came to my first discrete math class, there's just new territory for me. I didn't take Euclidean geometry in high school. I had not seen, I'm sure I must have seen a proof in like calculus or at least a derivation. But when I got to discrete math, I was shocked. I hadn't seen this before, and I just remember being sort of in awe of the proof that the square root of 2 is not rational. And now I look at it, it's a pretty it's a pretty straightforward proof. Actually, it's very, very beautiful. But anyways, the idea is that I want to provide some foundation for people that might be in that same situation. Also for computer science majors, because computer science majors also must take discrete mathematics. And in most universities, I think this is a requirement because you're dealing a lot with logic. And because when you're writing code, you're always, writing code is about logic, if then else, right? And so it's very, it's required. Discrete mathematics was a course that I've tutored computer science majors, so I know that much. Physics majors, maybe not so much in the undergraduate physics courses. I can't say for sure, but I know once you get to graduate school in physics, you'll be using theoretical mathematics to prove physics theorems or to be able to discuss physics. And so having a knowledge in this realm is important. And then also just for students who wish to compete in math competitions. If you are competing in a math competition such as the AMC 8 through 12, the Harvard, MIT math, or the Olympiads, you will have to write proofs. And so you'll have to be able to write proofs like even at a much higher level than even a mathematics major might be expected to in their first few theoretical courses. And then also anyone who's curious about learning mathematics. So as far as the content goes, if you don't have any mathematics experience, basically, we're not going to be using algebra. We're not going to be using calculus. We're not going to be using trigonometry. We may use some of the ideas for examples of proofs, but I think basically if you know nothing about math, you could take this course and learn how to use the techniques involved. Okay, so what are the objectives? First, you're going to become familiar with propositional logic, truth tables, and logical equivalents. To become familiar with mathematical notation, quantifiers, and other common symbols like the symbols for number sets and so forth. The student will be able to read, understand, and write various types of proofs. So those are the proofs I mentioned on the previous page. And the student will have a foundation of strategies for which to write mathematical proofs. So when you read a theorem or you read a corollary, you'll have an idea of different ways to approach it based on how the theorem is set up and what the conditions are. Okay, so one other thing the only other prerequisite that might be helpful is just knowing the different number systems, like real numbers, integers, natural numbers, complex numbers. We won't be going into any extended number system or into other fields. We'll only be dealing with either the complex number, I should say, the complex field and the subsets thereof. So that pretty much covers everything that most people already know. Except for, so I should just say, just the typical mathematical number sets. Okay, so a little bit about me. This is my picture. This is my name. I have a Master of Science in Math from Shawnee State University. Really excellent graduate program there. I definitely recommend it if you are a working adult and if you are sort of a person who thinks outside of the box and loves mathematics, then you should check out Shawnee State University. I have a Bachelor of Science in Mathematics from the University of Oklahoma. Here is the Bizzell Library where I lived, studied, and worked. I was a private tutor during my time there. And I can say the mathematics program at the University of Oklahoma is rigorous and thorough. So definitely not for the faint of heart. Currently, I'm wrapping up. I've gotten into, since I was exposed to basically applied research methods and quantitative methods as a part of my master's program. Hey, go back. I got interested in applications of statistics in that data science and business analytics. So for the past year, and yeah, for basically almost the past year, I've been studying data science through Harvard edX, and then started in March at Robert H. Smith School of Business through UpGrad. UpGrad is it's an online education delivery system that has professional certificates, master's degrees, and even a few doctorate degrees, a doctorate of business administration. It's been growing in the past 3 years, extremely large, millions of students, and it's got presence all over the world. I definitely recommend it because it's delivered online, and you also get access to the professors at the universities who have written the program, as well as other industry professionals. And it's one of these companies that's always asking for your feedback and then making use of them. So if you do decide to purchase a course through UpGrad, like I did, please use this code here, and I'll get some kind of referral bonus. So if you want to find me on LinkedIn, here is my LinkedIn. Please feel free to connect. All right, so let's go ahead and get started. So what I'm going to do now is switch my screen. Or yeah, here it is. And let me just also change the page color. And I prefer it to be darker. Okay. And I think now it would be okay for me to go ahead and pop the camera back on. See if I can just remember where to write so that I don't write on the picture. Okay, so we're going to start with introduction to propositional logic. So intro to propositional logic. By the way, this is a new pen, and I'm still not quite used to it. I'm much better at my other pen, so bear with me. So propositional logic, if this is how we write proofs, essentially. We can take a statement and we can say that this is a proposition. So we'll say a proposition or a mathematical statement. So let me just write down the first definition. So my first definition is a proposition, which I will also refer to as a mathematical statement. So this is a statement that has a truth value. So a proposition is a statement with a truth value. And that truth value is true or false and not both. So it could only be true or false, but not both or anything else. So the proposition is essentially like the atomic element. This is the smallest structure that we can have. Okay, and a truth value is assigned sort of in an arbitrary way. Essentially, at this point, we're not saying why something is true or why something is false when we look at creating logical arguments. Okay, we're only interested in the framework of propositional logic that says when you combine certain mathematical statements with certain logical operators, which I'm going to define next, then we get true or false statement. Okay, so we have the idea of a mathematical statement. The next thing that we need is a way to connect statements or propositions. And the way that we do that is with another definition. Wait, I want to use like the same size. So the next definition is for logical operators. So a logical operator is a way for us to connect two propositions, two or more. We'll talk about how many we can connect, but just for now, we'll say a logical operator comes in two forms. So first, let me just say a way to operate, this will be more precise, on propositions. Now that's sort of like what this is like when I ask students in class sometimes a definition, what is a logical operator? They'll say something that operates on logic. Yeah, so a way to operate on propositions. So when I say operate, I mean like change, let's say it like this, or combine propositions. Okay, that's probably more, what's the word? That's probably more enlightening. Yeah. So logical operator is a way to operate on propositions, meaning we can change or combine it. And we've got two types of logical operators. The first one is a unary operator. So this is why I said operate, because a unary operator, it doesn't combine two propositions. It acts only on one proposition. And typically, when we talk about propositions, we represent them by a letter. So let P be a proposition. And we don't know what P is. We know that it can be true or it can be false. Okay, so so now I will construct the first of several of what are called truth tables. So a truth table is just a way for us to examine the situations in which a logical statement, proposition, or whenever logical operators combine or act on some proposition, and then what is the truth value as a result. Okay, so first, I remember I made this class before, and this part was sort of time consuming, but it's fine. This gives you time to take notes, right? Okay, so I'm going to need more, but I'm going to just start with writing P in here. I'm going to choose green this time. Yeah. Okay, so P is my proposition from here. I said, let P be a proposition. Okay, so I've defined a proposition. Now, what can P possibly be? Well, P could be true or P could be false. Okay, so that's what we know about P. Now, a unary operator is an operator, it's a logical operator that acts on one proposition only. So the first unary operator that I have is called negation. And usually we call negation not. And actually you'll see it either written like this, with this sort of like, I guess, rotated. How would that be rotated? Like if you took an L and you rotated it and flipped it around, you'll see it written like this, but you could also see it written like a tilde, like this. Okay, so either one of these could be negation or not. And so what's the resulting truth value in either situation when we have the negation? Well, if we have P is true, the negation makes P false. And if we have P is false, then the negation makes it true. Okay, so that's the first unary operator. The next one we have is called the ID. And the ID is simply the identity. And so the identity operator in all of mathematics, you'll learn if you continue to study it, if you study real analysis, if you study abstract algebra, we have this idea of an identity or a neutral element that basically doesn't change anything. Or I think maybe like it comes from the idea from identity. It's like looking in a mirror, which is also the idea of reflexive, where A equals A. And so basically the identity just does nothing, and you could think of it also as sends the thing back to itself. So in this case, the unary operation of identity on proposition P just takes true to true and false remains false. Okay, now we come to a new one, which is capital T. And capital T is called a tautology. And we'll talk more about a tautology when I get into binary operators. But what a tautology is, it's a mathematical statement or logical proposition that's always true. And I could just give you an example, sort of an informal example, which is a statement that's always true. It is raining or it is not raining. So that's the idea of a tautology, something that's always true. And so how does that act on the logical operator? I gotta be quiet so I can draw a straight line. It makes everything true. So if it's true, true, and if it's false, true. Okay, and then the last one is called contradiction, which is, it doesn't matter what the truth value of the proposition is, it makes it false. Okay, so we have all of our unary operators and the resulting truth value on some proposition P. Okay, so now we come to binary operators. This is where it starts to get interesting. We can use binary operators to create compound propositions. So a binary operator, the word binary is meaning like two. So naturally, you can only combine two propositions, but you can combine two and then combine a third one to the two. And so actually, you can create pretty sophisticated and complicated compound propositional statements using binary operators by combining things two at a time. And there are actually quite a lot of binary operators. And so I will go about this in this way. And so I'm going to make the truth table and then simultaneously write down the definitions over here on the side. So first, let's start like this. And so I'm going to just construct the first truth, or the first column here. And let's let P and Q be propositions. Okay, so P and Q are both propositions. So I've got P, and then I've got Q. And now let me go ahead and fill in my logical operators. And I'll write the sort of name of them at the top. So I'm going to write basically all of them have a formal name and then an informal name or a name that's used in basically in the language of set theory. Okay, so the first one is called a conjunction. Or is it conjunctive? I think I'll just call it's a conjunction. And it looks like this symbol, and it goes by and. All right, and I think if I don't have straight lines here, I'm not going to be very happy about it. So let's just go ahead and construct the rest of the table. And then I'm going to go through afterward and give you the truth values. I don't want the arrow. This one. And let's see, am I going to run out of room? Maybe. Yeah, I think I am. So let me extend onto this. So then I'm going to extend it. If I'm in class, I can do this with a ruler. I guess, could I use a ruler on this? I think I tried it before and it wasn't effective. Let's see. Can I use a ruler? No, okay. All right, I think that's probably good enough. Okay, so just bear with me in the pursuit of my perfection here. Okay, so P and Q, actually I don't want to do that. So the first one is and or conjunction. Also known as and. Yeah, and it looks like this. Okay, so the next one is or, and this is called the inclusive or. We actually have an exclusive or, and I'll talk more about that when I get into the truth table. So this is called disjunction. Okay, and then we have, so we actually have the two disjunctions, and one of them is exclusive, but this one is called inclusive. And typically that's the one you're going to be using. It's not very often that you run across the next one, which is exclusive, and it looks like this. Okay, I think I got that correct. The next one is just called basically propositional. Well, we call it a conditional statement, or we call it if-then statement. So this one's called conditional. And the way that you think about it, or the way that we describe it, is if P, then Q, or you could also think of it as you could think of it as P implies Q. So P implies Q, and I just want to change this slightly. There we go. Oh, that's still not very good. Okay, so I've got to be very careful not to go down the rabbit hole of trying to make things perfect. All right, and then the last one over here, this one is called a biconditional statement. And this is basically an if-then statement that's true in both directions. So we call this biconditional. And we're going to spend some time talking more about conditional statements and the different ways that we can reform those. So this one is if P, then Q, and if Q, then P. And actually, we'll do our first proof of a theorem using this idea here. Okay, so now let's go through here, and first let's fill in the possible truth values and different combinations of the statement P and Q. So P could be true and Q could be true, P could be true, and Q could be false. P could be false and Q could be true, and then P could be false and Q then also could be false. Now, how many combinations will we have? Of course, we have 4, because we have 2. Basically, you can think of it like 2 to the 2. All right, and if we had more than that, then we could change the power. Okay, so now we get through we're going to go through each of these binary operators and talk about when they're true and when they're false. Okay, so the first one, wait, I'll have the eraser on. P and Q. This is only true in the case where P is true and Q is true. Okay, in every other case, it's false. And that's what we mean by and. We mean that both P and Q have to be true. If one of them is not true, if only one is true, then it's false. So in these two cases here, and if they're both false, then this P and Q is false. All right, and so right now, I'm not going to be giving any examples. I'm just going to be explaining the framework of the propositional logic, because here in just a moment, it's going to not make sense to you, I think, maybe. When I get to the if-then statement, it's going to be like, huh? So right now, I'm just looking purely at the structure of the propositional logic, and then later on, we'll look at examples. All right, so the next one is the disjunction or the or statement. And by or, we mean inclusive or, and I'll explain to you what inclusive or means when I contrast it with the exclusive or. So for the or statement, P or Q, when we're talking about inclusive or, we mean that this statement will be true if P is true, if Q is true, or if both are true. So this one is basically the opposite of the and statement. It's because everywhere, well, because it's true here. Yeah, it's true here. It's true here, and then it's false here. So what I mean by opposite is like it's got three truths and three truths and one false. And the and statement has three falses and one true. So this is or, and this is the typical or that you'll see. It's very rare that you'll see this one. And usually if you're supposed to use it, then somebody will tell you, or it will become obvious by the context of the problem. Okay, so and I think I'm not 100% sure, but I'm pretty sure I've seen this X or. Okay, so but that's like something might be used in like electronics or logic gates or something like that. Let me just look, since I can. Hold on a second, because I have the ability. So I'm pretty sure that XOR is exclusive or. Yeah, that's right. Okay. So, I mean, I just never use those symbols, but because I never use XOR. So, but let's explain what it is. So when is this one true? Well, this one is slightly different because it's an exclusive or. It's only true when P is true or Q is true. But if both of them are true, in that case, it's false. And that's where we get the exclusive part from. Because it's only true if one or the other is true, but not both. And definitely false if both of them are false. Okay, now we come to, so probably everything has made a lot of sense so far. And you've been like, yeah, that makes sense. Or maybe I've seen something like that before. And now we come to the propositional, the proposition if then. So our conditional statement, which is probably the most frequently seen. And usually in the mathematics, what we see is we see an if then statement, but of course one of the propositions will be a combination of these binary operators. So there'll be some condition like if this and this are true, then this or this, something like that. So it's not going to be just like P and Q. It's going to be some combination of statements combined with binary operators constructed to make P, and then another combination constructed to make Q. Or often Q might just be one statement because it's a conclusion that we're reaching. Okay, so let's talk about when is this true? If P, then Q. So it's definitely true if both P and Q are true. So P implies Q. if P is true, then Q is true, then P implies Q is true. And I'm going to skip this one next here. And I'm going to go down to, actually, let's not skip it. So the next one is if P is true and Q is false. So this is actually the only time this statement is false. And this is where it gets a little weird. If P is true, but it implies a false conclusion, then P implies Q is false. Okay, now the rest of these are true. And this is where it starts to get really weird if you're seeing this for the first time. Now, why is it true that P is false, but Q is true? And that's because if you start with a false premises, you can conclude anything. So if your assumption is false, like in these two cases, then your conclusion doesn't really matter. So these will always be true. And we'll look at some more examples of these. These ones are typically called vacuously true. And yeah, we'll get into that more later on. Now, I do need one more. Yeah, I need one more of these, actually. So I need to extend this because I want to explain that actually we can tell whenever the biconditional statement is true by looking at the forwards and backwards implication. So let's take a look at that next. Where did this? So let's connect the line. And let me make another nice line right here. Okay, so it looks like it got frozen in the middle. Back up. Okay, great. All right, so now the biconditional statement, like I said before, is sort of like saying that this statement has to be true forwards and backwards. And that means that P implies Q must be true, but then also Q implies P must be true, which is not always true. For example, I'll give you one informal example, and that is if it's raining, then the street is wet. Okay, so certainly it's true that if it's raining, the street is wet. But it's not always true that if the street is wet, it's raining. It could be finished raining, or it could be that somebody took a hose and sprayed it on the street. Okay, so that very informal example. I want to use very few informal examples because they aren't informal, but that's the idea here. So here, I'll give you another one that's even more concrete. So think about this. Every every square is a rectangle. Yes, that is true. Every square is a rectangle. Why is that? Because a rectangle is a looser definition, right? A rectangle doesn't have to be, it doesn't have to have all of the sides be the same length, but they do all have to be parallel, and all the angles have to be 90 degrees. A square, on the other hand, is not, so a square is always a rectangle, but a rectangle is not always a square. Okay, so that's the idea. Hopefully I made sense there. So then Q implies P here. And so if we want to talk about when is, so this is forward, this is backwards, and then we have the biconditional statements here. P implies Q, Q implies P, or we might say IFF, if and only if. So IFF means if and only if. So when are these ones true? So first of all, let's look at Q implies P. Well, it's the same thing as P implies Q, except we start by looking at the Q. So if both of them are true, this is going to be true. Now here's where it gets different. If the Q is false and P is true, then Q implies P is true. Here we're going to get false because Q is true and P is false, and then here we'll also get true. Okay, so when is P if and only if Q true? This is only true when both of these are true. So when this one is true and this one are true, then my biconditional will be true. So it's true here, and here it must be false. And then here again, it must be false, and it must be true here. Okay, so this is the completion of the truth table for the binary operators. And then from here, we're going to talk more about the conditional statement and different variations of that. But before I do that, I want to give you a taste of a proof based on what we know so far. And so what I'm going to do is write down a theorem. Okay, so actually first I need a definition. So my definition is logical equivalence. So I'll say that two propositional. Well, hold on a second. Let me erase this. So let's write it down like this. Propositional statements, or I'm going to call them compound statements. Are logically equivalent they're logically, maybe I should just try to write in cursive. Maybe not. That's horrible. I swear I'm not getting used to this pen. I think I'll go back to the bamboo, because I actually got used to that one. This one is very pointy or something. It's kind of strange. Okay, so two propositional statements are compound statements. So we're going to combine statements with binary operators, are considered to be logically equivalent when they have the same truth values. Okay, so let me show you what I mean by that with the following example. So my theorem is like this. So in mathematics, we get theorems. So we have definitions, which are something we don't need to prove. We often call those axioms or also postulates. And so axioms or postulates, these are things that we agree to be true and that do not need to be proven. So the very simplest and probably one of the first axioms is that there exists something that has no dimension, has no length, it has no width, it has no depth or breadth, is the language that was used, and that's called a point. So in order for us to be able to do any sort of geometry, there has to be something that exists called a point. If you don't have a point, then you can't create a line, which is between 2 points. If you don't have a line, you can't create a plane. If you don't have a plane, you cannot create any mathematical, a two-dimensional shape like a square or a circle or anything. So you have to have a starting point. In this case, of geometry, it's a point. We have to have a definition that we could all agree on from which we can start. Okay, so so we don't have to prove definitions, but theorems or corollaries, and often sometimes people use postulate as it's sort of inconsistent, actually, I think. I have seen postulates used where they had to be proven, but typically an axiom will never be used that way. So theorem is something that needs to be proven. And it should be the case that if you're in a mathematics course, or at least if you're a mathematics major, whenever you see a theorem, it will be proven to you, unless the theorem requires mathematical knowledge outside of the course's scope. Like, for example, I can think of a few cases in calculus where you kind of need like real analysis to prove something. But, okay, so whenever you see the theorem, that means what follows should be a proof. And so this is how, when you read a mathematical textbook, it should be like this: definition, theorem, proof, and then maybe examples like this. Okay, so my theorem is that P, if and only if Q is logically equivalent to, and I'm going to use this symbol here. I'm going to use this symbol for logical equivalence, is logically equivalent to P and Q. Wait a minute. Wait. Sorry, I got it wrong. Oops. P implies Q and Q implies P. Okay, so for, one thing that just struck me is that there is an order of operations to these operators. And it's called a binding strength. But essentially what it is that basically the unary operators have precedence. So let me just make a note here before I continue that we have operator precedence defined in the following way. Operator precedence, or what you might hear called binding strength. So this is similar to like the order of operations. Okay, so first we've got our negation, and then second would be our and, third would be the or, and then our implication and by implication actually would be the same level of precedence from left to right. So like this. Okay, so that I just want to say that now because I'm about to use because I have this compound proposition over here and I'm using parentheses and connecting them with this. So so that hopefully you probably looked at it and you were like, no questions asked. But you know, we've never discussed which operation should we do first. And usually you won't in a basic first discrete math course, but keep this note, and now we can go forward knowing that this is predetermined. And basically, it's kind of like the way you expect unary operators are conducted first, followed by binary operators, sort of like you apply a minus sign to a number before you multiply it, right? Okay, so how can we prove this? Well, we prove it with a truth table. So here's our proof. Well, let's see. Should I grab this truth table? Yeah, I think what I'm going to do is save some time here and go like this. Well, just messed up. Hold on. Let's see if I can copy this. What would happen? Here we go. Okay, let's try it again. Copy this guy and move it. And then I'm just going to change it a little bit to add one column for our and. Okay, so let me just erase this one. Yeah, perfect. Actually, yeah, it's fine. So what I'm going to do is I'm going to write this one here because there's room for it. And I'll write it in a different color. So this is the P and Q, or P implies Q and Q implies P. Okay, so basically it's actually quite simple. All I'm trying to do right now is show that this one and this one have exactly the same truth values at exactly the same time. I'm going to say time, but yeah, at the same location. You can say it like that. Okay, so let's examine it. We've already finished everything else, right, from before. So let's just examine this one. So when would this statement be true? P implies Q and Q implies P. This is going to be true exactly when P implies Q is true and Q implies P is true. So that's going to be here. Here it's going to be false because they're not both true. Here it's going to be false because they're not both true. But down here it's going to be true because they're both true. And you can see, like, this is precisely the same, which is what makes them logically equivalent. Okay, so P implies Q and Q implies P is exactly the same as P if and only if Q. And you can think of it like if and only if. Okay, let's see. The next thing I want to do might be, we can look at another example here. Actually, no, we're not gonna do that yet. So the next thing I want to do is get into looking at the conditional statement and basically the variations. So examining, and because looking at this conditional statement is how we get the idea for the different types of proof. So examining the conditional statements. So our if then. All right, so again, we're going to need truth table, and we're going to start by, so I think, yeah, maybe I can finish this and then we'll be finished for the day. So we're going to have P implies Q. Actually, let's just do, I don't want to waste my time trying to draw perfect lines right now. So P implies Q, that's an arrow. This is the conditional statement. Okay. P implies Q. And then we have Q implies P. So this one, this is called the, I just forgot. This is called the inverse. No, it isn't. See, I just forgot. Okay, so let me just call this one the original, I guess. The original. This one is called the converse, not the inverse. This is called the converse. And then we have, so let's see, I went from original to converse. Next, let's do not Q implies not P. And this is not Q implies not P. This one is called the contrapositive. This is a special one. And later on, I'll prove to you that these two are logically equivalent. And this is what gives rise to our ability to prove things using the method of contrapositive. Very useful. And then we have another one, which is not P implies not Q. And this is the inverse. Okay, and let me get rid of this. So these are, I wanted yellow. These are the variations of our conditional statement and different ways that we can affect it using our negation and just changing the order. Of particular importance here is to notice two things, and that is, first of all, that the original and the converse are not logically equivalent. And this is very common logic error that people make, where they think that if this is true, that implies this, then it has to be true in the other direction. So it's a very common mistake. Even after you've studied it for a long time, you might make that mistake. On the other hand, it is possible that they are true. And if they are, then it means that we have a biconditional statement. And actually, yeah. On the other hand, also, I said like on the other hand a lot. On the other hand, also this one, these two, the original and the contrapositive, are logically equivalent. Okay, so I'm going to stop here, and in the next lesson, I'll go through the truth tables of these different variations of conditional statements, and then we'll look at a couple of ideas about proving things by contrapositive like this. Okay, that's it for today. Hopefully that was helpful. And if you have any questions or if you notice any mistakes, please comment.